The total mechanical energy, E sub mech, is defined as the sum of the kinetic energy and the potential energy. So the sum of K plus U, where U is the potential energy function associated with the conservative force, with an appropriate choice of 0 point. If there are multiple conservative forces acting on the system, then U will be the sum of individual potential energy functions for each conservative force, with an appropriate choice of 0 point for each individual function. We've also seen that the change in the kinetic energy plus the change in the potential energy is equal to the change in the total mechanical energy. And that's just basically the derivative of the equation that I wrote above. Right? And this change in the total mechanical energy will be 0 for conservative forces. In addition, we've seen that the change in potential energy is related to the conservative work done in the system, so that W sub C, the conservative work done, is equal to the negative of the change in the potential energy. But we also know that the total work done includes both conservative and non-conservative forces. So the total work done is equal to the sum of W sub C, the conservative work done, plus the non-conservative work done, and that total work is equal to the change in kinetic energy. Now, I can rewrite that equation by rewriting the conservative work in terms of the potential energy. So I could write this now as the non-conservative work minus the change in the potential energy is equal to the change in the kinetic energy. This is, again, just a restatement of the work kinetic energy theorem. Now, by rearranging this equation, this means that the non-conservative work is equal to delta K, the change in kinetic energy, plus delta U, the change in potential energy, but that's equal to the change in the total mechanical energy. So the non-conservative work is equal to the change in the total mechanical energy. This is a sufficiently important result that I'm going to write it by itself in a box. So the non-conservative work is equal to the change in the total mechanical energy. So what we've shown here is that the result of any non-conservative work on the system is to change the total mechanical energy of the system. Now, if there is no non-conservative work, if the forces acting on the system are all conservative, then the total mechanical energy remains unchanged. Delta E mech is 0, and we say that the total mechanical energy is conserved. Now, if there is a non-conservative force, it turns out that in most cases the work done by a non-conservative force is negative, resulting in a negative change in the total mechanical energy. In other words, in the removal of total mechanical energy from the system. It's lost from the system. Now, we've been talking here only about mechanical energy, which we've defined as the sum of kinetic energy and potential energy, but one can also talk about non-mechanical energy, the most common example of which is loosely referred to as heat. As an example, in the case of friction, which is a non-conservative force, we know that the action of friction generates heat. What's happening is that the non-conservative work done by friction is negative, and therefore is reducing the mechanical energy, the total mechanical energy, according to this expression. But where does that energy go? We said that it's removed from the system in terms of mechanical energy. That's true, but we can think of it as at the same time causing an increase in the non-mechanical energy or the heat energy of the system. So if one were to keep track of both mechanical and non-mechanical energy, then it turns out that the total energy, mechanical and non-mechanical, the total energy of a system is conserved even if non-conservative forces are acting. However, it's difficult to recover the non-mechanical energy and change it back into mechanical energy. These non-conservative processes are not reversible. This is a complicated topic, and it's the province of more advanced courses in thermodynamics or statistical mechanics, which you may encounter later. In this course, we will confine our attention to mechanical energy, the sum of kinetic energy and potential energy, and we'll treat non-conservative force as removing or adding mechanical energy to the system.
In problem solving, when we're working with problems with potential and kinetic energy, remember we have our main concept that the non-conservative work causes the potential energy and kinetic energy to change. K final minus K initial plus U final minus U initial. Now, how are we going to apply this in problem solving? Well, what we'd like to introduce is a tool which we're going to refer to as our energy state diagrams. So the way this works is let's have an example to think about. Suppose you have a dome. So here's some dome. We can think of this as the MIT dome. And you have an object that is initially at the top of the dome, and then this object is sliding down the dome, and at a later time, it's at a point somewhere along the dome. Now, eventually, it's going to fall off the dome, but that's a separate question. So how can we use our energy ideas to analyze this situation? And the way we do it is that we choose first initial and final states that we're considering. Because our first idea in the energy diagram is to compare the change in energy, kinetic energy between the initial and change of potential energy between the initial and the final states. So in our dome problem, we would choose our initial state. Let's draw our object at the top. And in our final state, separately, let's draw the object over here. And then we want to parameterize these states by some type of coordinate system. So here we're going to have some type of coordinate system that we'll use for both. Energy is a scalar, so we don't have to worry about it. And what I'll do is I'll define an angle theta final. Here from the vertical, here theta initial is 0. And I've now parameterized my initial and final states. Now, the important thing that we'll do in the energy diagram is to choose our 0 potential energy. Where are we going to choose this? So we could say either a surface, we'll call that potential energy. And in this diagram, I can choose my 0 for potential energy anywhere I want, but I want to draw it on my initial and my final states. So I'm going to choose it right here, and I'll denote this as U equals 0. And now I can now make a list of, I want to identify, so step 3 is to identify the K and U for each state. So here we have K initial, it's at rest, 0. And U initial, well, I didn't introduce a parameter R. It's U initial is how high the gravitational potential energy. So in this particular case, mg times R. Now over here, K final is 1/2 mv final squared. And U final, we can denote it here. If I plot this out, and that's R, then you can see that this is R cosine theta final. So that's mg R cosine theta final. Now the fourth step is to identify W non-conservative. Is there any non-conservative work? Now here, let's assume the dome is frictionless. And that means that W non-conservative is 0. And our last step 5 is we can apply the energy principle, which is W non-conservative equals delta K. Let's write it out, everything explicit now that we've defined K final, minus K initial, plus U final minus U initial. And you see the power of these diagrams is, and this methodology is, we've now defined very explicitly every single term that appears in the energy principle. And so we can write out our result that 0, K final, 1/2 m V final squared, K initial, 0, plus U final, mgr cosine theta final, minus U initial, mgr, and there we have applied the energy principle using the tool of energy diagrams. Let's consider an example of motion in which we want to use our energy concepts. So suppose we have a ramp, which is circular, radius r, and we have an object here. And now here's a surface, a certain distance d, that has friction, where the coefficient of friction is non-uniform. So we'll write it as mu naught, and we'll write it as mu1 x. We'll take x equals 0. And then here, there's a spring and a wall. And here, there's no friction. Now, as we drop, assuming we have enough height here, h, so that this block will slide across the friction, make it all the way across, and start compressing its spring, what I'd like to find is how much the spring has been compressed. OK, now how do we analyze this? Well, the key is to use our energy principle, where we have W external equals the change in mechanical energy. And the key is to, what we're going to do is the tool that we're going to use is what we call energy diagrams for the initial. So what does this mean? We want to choose, we want to first identify the initial and final states that we're referring to. So in our picture, here's our initial state. And I'll draw the final state in when the spring has been compressed a distance x final. So I drew it on my diagram. So we have initial and final states. And now what we want to do is choose reference points, 0 points, 0 point for each potential function, and show that on our diagram. So for the potential energy of gravity, here, if we chose this to be y, then this is y equals 0. And u at y equals 0 is 0. And we'll call that the 0 point for gravity. And the 0 point for the spring is when this x, now I'm going to call here x equals 0, so let's call this a variable. I can call it anything I want. I'll call it u final. And this is where u is 0. So u final just measures the stretch of the spring. And so at y equals 0 is 0, and u spring at little u equals 0, 0. So now I can identify my energies. So let's talk about the initial energy is all gravitational potential. That's mgy. It's starting at rest. And E final, well, here, this is the distance where it comes to rest also. So there's no final kinetic energy. There's no gravitational potential energy because we're on the surface at y equals 0. But our spring has been compressed by 1/2 k little u final squared. Now, in terms of our external work equals the change in mechanical energy, we have now identified the right-hand side using these tools of the energy diagrams, and I can write my description u final squared minus mgy. Now what I have to do is think about the friction force, F kinetic friction, as the object moves. This friction force is non-uniform. If we were to draw N and mg, then our friction force here is equal to the integral minus the integral from x equals 0 to x equals d, x equals 0 to x equals d, of the friction force, which is equal to the coefficient of friction, mu k n dx. Now, that 0 to d, notice that our coefficient of friction is varying. And I chose that intentionally to show you that friction is really an integral. So we have mu naught plus mu 1 x mg dx. Let's put our integration variable in there. And these are just two separate integrals. The first one is easy. It's minus mu naught mg d. And the second one is minus mu 1 mg. And we're just integrating x prime dx prime between 0 and d. So that's simply d squared over 2. And that's equal to k u final squared minus mg y. Let's write that as y initial. And we're starting it at y initial equals h. And so even though this is complicated, I can now solve for how much this spring has been compressed with a little bit of algebra. And so I'm just going to bring a bunch of terms over to the other side and take the square root of 2 divided by k of mg y initial minus mu naught mgd minus mu 1 mg d squared over 2. And that's how much the spring is compressed. Notice what I did not do was divide this up into a bunch of different motions. I picked an initial state. I picked a final state. I drew my energy diagrams with my 0 points. I described the key parameters of the initial and final states, yi and u final. I defined the initial mechanical energy, the final mechanical energy, and then applied the work mechanical energy principle. I had to integrate the friction force because it was non-trivial and solve for how much the spring has been compressed. When solving physics problems, we have fundamental principles. For instance, we have Newton's second law, and we also have an energy principle. Work non-conservative equals the change in kinetic energy plus the change in potential energy. And many times students are challenged by, do I use this law? Do I use that law? Why do I use one or the other? Do I use both at the same time? Can I get the same answers, etc.? Now, I want to illustrate a particular category of problems where we have some type of circular motion and why we need to use both of these laws. So let's go back to our dome example at MIT. And let's say we have an object that's on the dome. And now let's write out a free body diagram for this object. So we have our gravitational force. We have a normal force. And here, let's just assume that our dome is frictionless for simplicity. So what you see here is that the object is displacing in a direction, now here if I choose r hat and theta hat, and if I choose a coordinate system where I take my positive angle theta this way, that the normal force and the displacement are perpendicular. Now, what that means is that the work done by the normal force, F normal dot ds, is 0 because, well, we're calling F normal equal to the normal force, and that the normal force is perpendicular to the displacement. So what that means is all information about the normal force is not included in the energy principle. In fact, the energy principle is the work that's done is just the amount. This is angle theta, so this is angle theta. So the actual work done by the gravitational force, G, is the component of G, mg sine theta, times the displacement ds. So the only work that's appearing here, and this is conservative, and so when we integrated this work and got that the work done by the gravitational force is minus the change in potential energy, that's showing up here. So the part of the force that's in the direction of the motion is giving us the energy condition, but we're losing all information about the forces in the radial direction. So we also, because also what we need is Newton's second law in the direction perpendicular to the displacement. Displacement is in the theta hat direction, so we need Newton's second law in the radial direction. And that we have, r hat, is we have a normal force minus mg cosine theta, and the object is undergoing circular motion, so it's equal to minus m v squared over r, where r is the radius of the dome. This equation is not at all included in the energy condition. You may say, well, what about the tangential Newton's second law, which is mg sine theta equals m r d squared theta dt squared. But it's precisely this equation that's integrated with respect to the displacement, and that gives us our energy principle. So in summary, the energy principle is the integration of Newton's second law in the direction of motion, and we're completely missing the application of Newton's second law in the direction perpendicular to the motion. Energy does not account for that, and that's why we needed separately to apply both of the principles of energy and Newton's second law in the radial direction in order to figure out how to solve this problem. Now, this idea is true in general. When you have circular motion, you need the energy equation, which is the tangentially integrated Newton's second law in the tangential direction, and you need Newton's second law in the direction perpendicular to that circular motion.